Welcome to 34th session on measure theory, 6th session on LP spaces. Today we will, whatever you call LP norm, we will prove its interior norm, and then we will show LP spaces are complete with respect to that. In this lecture, we will be confining our P to be 1 less than P less than infinity. Okay, so let us get started. So yesterday we proved Young's inequality in the last session. If A, B are non-negative and 1 less than P, Q less than infinity, so that 1 by P plus 1 by Q equal to 1 conjugate indices, then we proved that AB is less than or equal to A to the power P by P plus Y to the power Q by Q. Also this we proved by considering this function f of x equal to x in xy minus x to the power P by P, right? Then we proved that point of maximum was at x naught, where x naught to the power P minus 1 is y, right? Therefore, from that we concluded my AB is less than or equal to A to the power P by P and Y to the power Q by, let me stick to x first so that it will be easier. Xy is less than or equal to x to the power P by P plus Y to the power Q by Q, and equality holds at x naught. Okay, but what is x naught? X naught is y to the power 1 by P minus 1. Therefore, raise both sides to power P. Then I have x power P. I will replace x naught, x power P by y to the power P by P minus 1, which is y to the power Q. So, equality holds in Young's inequality. If and only if x to the power P equal to y to the power Q. Okay. So pause, review, proceed. In the last section I was not sure about that, whether there was some constant or something. You will see the reason for my confusion there. Okay, now this is okay, right? So I will stick to now A and B. So AB is less than or equal to A to the power P by P and B to the power Q by Q. AB are non-negative. Okay, because x I want to use for this. Okay, so I don't want to use x here. Okay, that's Young's inequality, right? So what we want to prove is Hölder's inequality. I think I proved it in the last session, right? Yeah. What did we do? Hölder's inequality Z, and if let f g from x to x be measurable. I don't want to write because it may be R extension or R or C, so it's just measurable functions. Then integral of mod fg is less than or equal to LP norm of f into LQ norm of Q, right? This we proved by integrating. How did we do that? We simply did, what we did was we looked at A to be fx mod fx, okay, because it has to be positive, LP norm of f, and B to be mod gx by LQ norm of G. Therefore, AB will be mod fx into mod gx, but it's mod fx by LP norm of f into LQ norm of G. AB will be less than or equal to, okay, what is that? A to the power P, that is f mod fx to the power p by this to the power p plus 1 by p, and 1 by q mod gx to the power q by LQ norm of g to the power q, right? So integrating, what we get is mod f g by LP norm of f into LQ norm of g, right, will be less than or equal to, I have to integrate this, then this constant comes out p, and I am going to integrate this power p, but these are the one and the same, therefore it's 1. Similarly, this will be 1 by q, which is equal to 1, right? Therefore I get integral of mod f g is less than or equal to LP norm of f into LQ norm of g, right? So this I think I proved in the last session. I was not sure, so I just repeated the proof because I want you to discuss the equality case. When does the equality hold in Young's inequality, or Hilder's inequality, sorry. Right. Now if you go back, you will see what I am doing. So if equality hold, that means these are equal, right? That means what I am going to do, I am going to get something like this. Okay. So equality holds. If only let's look at this. What we did was mod fg by LP norm of f and LQ norm of g equal to 1 by p mod fx to the power p by LP norm of p to the power p, and 1 by q into, this is again integral. Okay, I'll come to that. So I can take this out, right? So this side is supposed to be greater, therefore if I take this 1 by p integral of mod fx to the power p by LP norm of f to the power p plus 1 by q into integral mod gx to the power q by LQ norm of q to the power q minus integral mod f g by LP norm of f into LQ norm of g. This is greater than or equal to 0. Is it okay? So this equal to 0 implies this integral must be 0. That is 1 by p into LP norm of p to the power p mod fx to the power p plus 1 by q into mod gx to the power q by LQ norm of g to the power p minus 1 by mod f to the power p mod LP norm of f into LQ norm of g into mod f g. This integral is greater than or equal to 0, and now we are claiming it's equal to 0. Is that okay? So now notice that if this is equal to 0, that means integrand must be 0 almost everywhere. Because this is a non-negative function and it is integral 0, that means integrand must be 0 almost everywhere, of course, with respect to the measure mean. Okay, what does that mean? That means fx to the power p by f power p, that is 1 by p plus 1 by q mod gx to the power q by LQ norm of power q right, equal minus mod of g fx gx by this is 0 almost everywhere. Okay, is that clear? Notice that this is something like 1 by p a to the power a to the power p plus 1 by q b to the power q equal to ab, right? So we know that this happens if only a to the power p equal to b to the power q, right? That means fx to the power p by to the power p equal to gx to the power q by norm of gq to the power q, right? This is almost everywhere. Okay, this is true for almost all x, or this is true almost everywhere, right? Therefore it says mod fx, there is a mod, I'm sorry, to the power p into this some constant. Think of this as a constant a equal to, think of this as a constant b into mod gx to the power q. Notice that a and b do not depend upon x. They are the norms of LP norm, p to the power LP norm of f, and this is q to the power of LQ norm of g. That is where a, and this is where b. Okay, this holds almost everywhere. Therefore, what we have concluded is equality holds in Hilda's inequality if and only if there exist constants a and b, so that a mod f to the power p equal to mod b mod g to the power q, almost everywhere. Okay, so pause, review, proceed. See, these are the small things which usually is never done in classes. It's very easy to check from that and then leave it. I also thought of glossing over that, but then I decided to give a complete way of complete analysis. Okay, I hope you like it. So the next thing we want to prove is using Hilda's inequality. Notice that again the equality hold is exactly similar to Cauchy-Schwarz inequality, right? If you have inner product space, then modulus of x dot y, that is inner product x y, is less than or equal to norm x into norm y, and equality holds equal if x and y, okay, there are scalars so that y is a multiple of x or x is a scalar multiple of y. It's something very similar to that. In fact, in the case of p equal to q equal to 2, we will actually get that. Okay, right. Let's now go to the next result. Let me see, trick to screen share, yes. So next thing is we want to prove Minkowski inequality. So what does it say? Let f and g be in LP of x be mu, which is for us LP 1 less than p less than infinity. For p equal to 1, p equal to infinity, we already proved whatever we wanted to show. LP norm of f plus g is less than or equal to LP norm of f plus LP norm of g. So this is nothing other than triangle inequality for the norm. Once we prove this, then it actually becomes a norm, because other properties of norm we already proved it. Okay. Okay. So let alpha equal to norm of f plus g, right? Therefore, alpha to the power f is nothing other than mod f plus g to the power p. Is that okay? So the only thing you have to remember, usually I only thing I remember is that f plus g to the power p, you write it as f plus g into f plus g to the power p minus 1, and this is less than or equal to mod f into f plus g to the power p minus 1 plus mod g into f plus g to the power p minus 1. Do you understand this? Yeah. Why do I need? Because I want to use Hilbert's inequality. If you remember, Hilbert's inequality says this is not the same f and g. Mod f g is less than or equal to LP norm of f into LQ norm of g. Right? For q, to get q, I need p minus 1. Right? 1 by p plus 1 by q equal to 1. Therefore, 1 by q equal to 1 minus 1 by p. I am just writing so that I will remember. Therefore, my q must be got as p by p minus 1. So, I am going to get something here. Okay. Now, in a typical classroom, I give this and ask my students to apply Hilbert's inequality for each of these things. For that is, I have integral of mod f into mod f plus g to the power p minus 1. So this is my f, g is mod f plus g to the power p minus 1. For this, we apply Hilbert's inequality and simplify. Okay, I am going to do it, but many times there are too much of symbols, people get confused. So it's easier if you do it. Okay. If you are not very confident, you can watch. So, therefore, alpha power p is less than or equal to integral of mod f into mod f plus g to the power p minus 1 plus integral of mod g into mod f plus g to the power p minus 1. So, I want to look at each one of them. Okay. So, let us look at integral of mod f into mod f plus g to the power p minus 1. This is by Hilbert's inequality. Okay, less than or equal to LP norm of f into mod f plus g to the power q times p minus 1. Right? What? This is your something like g. Therefore, I have to compute the LQ norm of g. That means raise it to the power q. Right? Therefore, q, the whole thing to the power 1 by q. Is that clear? Now notice that I already said this 1 by q equal to this. Therefore, cross multiplying, you will get p equal to p minus 1 into q. Are you following? Yeah, that is the trick. Therefore, this is nothing other than LP norm of f into f plus g. Okay, this is f plus g to the power q, and whereas it has to be 1 by q. Are you following? F plus g, q into p minus 1, q into p minus 1 is p. Maybe I will write it mod f plus g, so that I will also remember properly, to the power 1 by q. But if I want LP norm of f plus g, what should I do? I have to take it to the power. I have to take the pth root into, okay, this is LP norm of f plus g to the power p by q. Right? This I want to write it 1 by q, but I am going to write it 1 by q. Am I clear? So this I have to take to the power 1 by p and then take this. But it is only 1 by q, therefore I have to multiply by p. Is that clear to you? Okay. Right? Similarly, this mod f plus g to the power p minus 1 is less than or equal to mod g to the power p and integral of, sorry, not integral, f plus g pth norm of f plus g power 1 by p by q. So what you have shown is alpha power p, that is norm of f plus g to the power pth norm of p to the power p is less than or equal to LP norm of f and LP norm of g multiplied by, this is what? Okay, this is alpha to the power p by q. Yeah. Therefore, divide. And again, as usual, when I want to divide, you can see, okay, if this is equal to 0, okay, then this is also 0, right? Therefore, there is nothing to prove. Okay, sorry. I want to say something else. F plus G. So, the only case we want to prove is this is what I want to divide by. Yeah, right. Right. Okay, if this is equal to 0, this is automatically correct. Therefore, I can assume this is not equal to 0. Therefore, this quantity is not equal to 0. Therefore, I can divide by that. Therefore, it is alpha to the power p into 1 minus q. Right? Divide this by this. Is that okay? That is less than or equal to LP norm of f into LP norm of g. But what is this? P into 1 by 1 minus q is same as p into 1 by p, which is 1. Therefore, it is alpha. Alpha is less than or equal to LP norm of f. So, we have proved Minkowski inequality. So, finally, we have proved the LP norm is actually a norm, right? The next thing we want to prove it is the LP space is complete with respect to the LP norm. The proof is exactly similar to the way we proved L1. Okay, except as you can see here, I have to raise to the power p, 1 by p, etc. Okay, it will be little intimidating to use that power. Okay, so I will recall how we proved completeness of L1 quickly, and we will use the same trick here. It's always good to revise. So remember, if I have a vector space, this is a non-linear space. Okay, we proved this is complete if only if every absolutely convergent, that is norm convergent. Series is convergent. What does that mean? If I have a sequence xn in x and summation norm xn is finite, then that implies summation xn is convergent. That means partial sums xn 1 to n of xk, it converges to some element x in x. So it's converged. Then x we call as the summation. Right? So this way is a separate video. Okay, when is a norm space? When is a norm linear space complete? Okay, there is a video under functional analysis playlist. We more or less proved it in the case. Okay, right. So what we want to prove is, let's take LP, let Fn be a sequence and assume LP norm of Fn is finite. Then I have to prove summation Fn converges to F in LP. What does that mean? There exists an F in LP and such that this converges to F. That means the partial sums, namely k equal to 1 to n of Fk, F minus this in LP norm goes to 0. Okay, limit of this is 0. This is what I have to prove. Is that clear? Pause, review, proceed. Okay, how do I prove that? So let us start with the proof. So what is given? I am given LP norm. Again I am assuming 1 less than p less than infinity. Okay, n LP norm of this is finite, right? So let me define Gn. So the only thing I remember is this proof uses monotone convergence theorem and dominated convergence theorem. Right? When I want to say monotone convergence theorem, that means I have to think of some sequence of positive functions. Right? So obvious thing is this one, mod f1 plus mod f1. Is it okay? Right? Now therefore my this Gn, yeah, okay, is that clear? Okay. Now notice that LP norm of Gn is less than or equal to LP norm of Fk, k equal to 1 to n, but that's less than or equal to all over 1 to infinity of mod LP norm of, these are all P, LP norm of this, which is finite. Therefore for each n, Gn belong to LP. That we know because Gn is a vector space, therefore no problem. Right? Okay. Now notice that Gns are non-negative, therefore, and Gns are in LP, therefore GNLP that converges to something. Okay, call it G. Okay, then G will be measurable and G will be non-negative. Right? But since the non-negative, I can write it as G power P. Okay, therefore G power P will also, G will also be non-negative and measurable. Okay, we can write as yes, G power P, where G is measurable, non-negative. Is that okay? Right. Now notice that by monotone convergence theorem, okay, Gn power P converges to, increases to G power P. Right? These are all non-negative things. Therefore, integral of Gn power P, limit of this must be equal to integral of G to the power P by monotone convergence theorem. But notice that each one of these fellows is less than or equal to, okay, maybe I should have said, let us call this as M. Let M equal to this. Okay? Right? Therefore, let us look at mod Gn to the power P, LP now. Okay? Gn is positive, therefore I don't write, right? Gn to the power P, that's less than greater than equal to M to the power P. Because notice that my Gn is less than equal to this fellow, but this is less than equal to M. Yeah? So this to the power P will be less than equal to this to the power P, this to the power P, and so on, M to the power P. Yeah? So what I have shown is, therefore, G power P integral is less than equal to N to the power P. In other words, G is also in LP. So pause, review, proceed. So what you have shown is my Gn, okay, n equal to 1 to infinity, okay, converges to G almost everywhere. Or yeah, converges. Okay, right? But what is this? My Gn is nothing other than mod f. Sorry, it's equal to, not converges when I say equal to this one, right? Okay, and this is this is true. Therefore, what does it mean? That means mod fn of x equal to g of x for almost all x. Okay, is that clear? Where does almost everywhere come to? Because what I know is integral Gn, okay, to the power p is convergent. Therefore, I know Gn to the power, this G to the power p is finite almost everywhere. Right? You understand that? we have to remember if f is integrable and non-negative, not necessary anyway, then f is finite almost everywhere. That's what we are using. That's why the almost everywhere comes here. Is that okay? Now, since this is series for each x where this is convergent, then this is absolutely convergent series. Therefore, it is convergent, right? Therefore, f1 of x converges to fx for all x not in the exceptional set. Call it E. That is for all x not in E, where mu of E is 0. Is that okay? Right. Now notice that mod fx is less than or equal to gx, therefore f belongs to LP. Because to the power p will be g to the power p. Okay? Therefore it is in LP. Now we want to prove f1 converges to f in LP. Now we already know f is in LP, so I have to say f1 converges to f in LP. So what does it mean? I have to show mod f1 minus f to the power p, that goes to 0. But notice that fn converges to f almost everywhere, right? For x not in E. Okay? And so to make sure of this convergence, what I will require is I want to use dominated convergence theorem. That means I have to look for a function which dominates this. That is very easy. Mod fn minus f is less than or equal to mod fn plus mod f. But each one of them, this is less than or equal to mod gn plus mod f, but that is less than or equal to g. And this is less than or equal to g plus g, which is 2g. Right? Remember, gn increases to g. Therefore, mod gn will be, there is no mod, it's actually gn. Gn is less than or equal to g. Therefore, it's less than 2g. And that. Is that okay? Therefore, when I want to check thing, therefore mod f1 minus f to the power p is dominated by 2 to the power p and g to the power p. Okay, this is an L1 function, right? Therefore, this integral f1 minus f to the power p goes to 0. So, what you have shown, your LP norm of fn is finite, implies there is an f in LP, so that fn equal to f in LP. You understand the meaning? Take the partial sums. Okay, this will be in LP. This sequence of functions Sn converges to f, that is f minus f in LP norm goes to 0. This is what we prove. So, how does it prove it's complete? Let's go back. How did we prove in L1? See, what we did was for each k, okay, we chose an nk so that norm of fn minus fnk, or for all n and m greater than or equal to nk, norm of fn minus fm is less than 2 to the power minus k. Alright, in particular I chose nk itself. So I chose nk so that it's an increasing sequence. Therefore, what we did, I'll quickly recall. Okay, suppose f1 is Cauchy, right? Then for each k there is an nk, so that nk plus 1 is greater than nk, and modulus of f for on n and m greater than or equal to nk, fn minus fm and p is less than 2 to the power minus k. Right? Therefore, what it will do is we look at fn1 and we define g1 equal to fn1, g2 equal to fn2 minus fn1, and gk equal to fnk minus fnk minus 1, etc. Now, if I look at norm of gn, okay, you can see this will be gk. You will see this is given to to the power minus k, which is convergent, right? Therefore, what I have shown is this, given in a Cauchy sequence f and Cauchy sequence in LP, we found a subsequence f and k such that summation arm of f and k is convergent. You understood? This is pth norm. Therefore, by the earlier observation, that means there is an f in LP such that f and k converge to f in LP. Okay. Now it's a general fact in metric space. If I have a sequence Cauchy and you have a subsequence in x and k converge to x, then x and converge to x. So I quickly recall, because we have done it already in L1. Sorry, I forgot to screen share. Let me go back. Yeah. Suppose F1 is Cauchy, then for each k I can choose an nk such that nk plus 1 is greater than nk, and for all n and m greater than nk, LP norm of F1 minus Fm is less than 2 to the power minus k. Then I define G1 to be Fn1, G2 equal to Fn2 minus Fn1. This is what we did in L1. And Gk to be Fnk minus Fnk minus 1. Then by construction, some infinite series now LP norm of Gk is less than or equal to infinite series to the power minus k. Therefore, this is convergent. Right? Now, let's go back to the just now proved result. Since this is convergent, then I know there exists. That means what I have shown, there exists subsequence f and k such that LP norm of f and k sum it over, then that is convergent. Okay. Therefore, by the last result, there is an f in LP such that f and k converge to f in LP. Right? Okay. Now, how does it help? Fn is Cauchy in LP, and there is an f in LP and a subsequence, maybe I should say subsequence f and k and f in LP, so that f and k converges to f in LP. Okay, that means f and converges to f in LP. Why does it follow? That is the metric space result. If xd is a metric space, xn is Cauchy. If I know there is a subsequence x and k which converge to x, then xn converge to x. Most often when you prove any Cauchy sequence of real numbers is convergent, this result is what you used. Okay. So we have proved the LP space x b mu, okay, with LP norm is complete. For which p, remember, for 1 we proved, for infinity also we proved, therefore we proved for all p. Okay. Okay. So now let me rush through. So this all bounded functions in LP, okay, they say the space of bounded function LP is dense in LP. Exactly the same way I proved in L1, and the space of simple functions in LP is dense in LP. And in the case of one less, this let me write, this is 1 less than p less than infinity. Okay, I want to make sure that is less than infinity. Okay, in general it may not be true for p equal to infinity. And then for 1 p less than equal to p less than infinity, and my x equal to r, b equal to m, and mu equal to a Lebesgue measure, then step functions in LP, that is dense in LP. The proofs are exactly similar. Okay, the only thing you should remember, okay, you should attempt the proof. Okay, go back to analogous result L1 and modify it. for LP. Notice that you had already done it in when you did perhaps several variable calculus, analysis, RN, or whatever you want to call it. You remember? I'll just indicate, because this is why I keep saying it's always good to revise things earlier so that you know, oh, the proof should be something similar. Then I feel confident I can do it here. Okay, I'll just indicate and stop. Suppose I have R2, I have a sequence x and yn. Okay, then I want to say x and yn converge to xy. We know that if only xn converge to x and yn converge to y. One way is easy. The other way around, what do you do? I have to estimate x and yn minus xy, the norm. Right? Now, what you know is this norm involves xn minus x whole squared plus yn minus y whole squared, and then taking a square root. Right? Then what did you do? I want it to be less than epsilon for n greater than or equal to some n naught. Right? That means I want it to be x squared. This should be x squared by, right? You understand this? This will be 2f squared. Okay? That is possible. Then I have to divide by 2, because I will get x squared plus x squared, 2f squared. When I take square root, it will be epsilon square root 2. Therefore, what I can do is use the convergence. Okay, so that mod x and minus x is less than epsilon by square root 2. Epsilon squared by square root 2. Or epsilon by square root 2. Right? And similarly, yn. Then you will have, this will be less than epsilon squared by 2, epsilon squared by 2, etc. etc. Okay? So, exactly the same thing, mod fx to the power p, and then integrate to the power 1 by p, but the idea is the same. Okay? Take at least one proof. For example, the set of simple functions LP is dense in LP. Okay? Look at L1, keep it, okay, keep it in a paper, pen and paper, and another, take another blank sheet and try to modify the proof. Okay, that's the best way to learn. Okay, so we have come to the end of measure theory. I hope you got some kind of ideas and you understood some of the basic tricks of the trade. Okay, and as usual, my lectures are not polished. As you can see, I have been struggling and thinking, okay, I am doing it. My only thing is that you should be part of this thinking process. You would have liked it. Okay, and I don't, as I said, I don't plan to take up abstract measure theory anymore, in the sense like, you know, a sign measure, complex measure, and Radon-Nikodym theorem, and dual of LPs, and then differentiation. Okay, one of the most famous results of Lebesgue, he characterizes when a function is indefinite integral of an integral function, when g is of the form a to x f of t dt. Okay, f is integrable. Okay, he had characterized things. We had some kind of a glimpse. We talked about indefinite integral before fundamental theorem of calculus. I derived some 3 or 4 properties. Please go through it. But I don't plan to pursue it, because in my opinion, most measure theory is to some extent is a basic culture, and it should be a core course which should be taught in one semester. So that if you want to go to higher aspects, okay, not necessarily work in measure theory, you have enough tools and material which you can use in other parts of mathematics. If you go to functional analysis, PDE, harmonic analysis, you should be able to do it. Okay, if you know these things very properly, you should be able to learn advanced stuff much more easily. Okay, I wish you all the best. Take care. We'll meet again on some other occasion.